Good morning. Welcome to our presentation on thermomechanical coupling, induced performance degradation with storage systems. My name is Sanjeev Sondur, and I and Kenny Gross and I are from Oracle Corporation. Dr. Kant is from Temple University, US. We'll be talking about today's presentation on what we studied about the thermomechanical coupling in storage systems, in particular to backup and retrieval systems. That's where predominantly the hard disk-based secondary storage comes into place. We'll talk about the basics of the problem, that is the anatomy of a backup system, the hidden inefficiencies. It's completely latent, completely visible. Everybody knows about it. It's dominantly studied, but it is so hidden that to collectively it degrades the performance of the storage system. And by doing that, it causes problems and results in SLA violation and quality of service violation. That's very critical of this. So although these are backup and retrieval systems, why is it critical? Where is the SLA and the QoS violations so stringent coming? Where are the tables, the data for this? And with respect to this, we'll talk about the studies we did in Oracle data labs, and we looked at what we studied, what data we collected, what workloads we executed, and what were our observations, and why did we do it. And based on the observations, we'll look back at the root cause of these inefficiencies, and we'll talk about in detail the mechanical, thermal, electrical intercoupling, and why is this intercoupling so strong? Why is it necessary to study them together than as single individual pieces? Based on that, we'll talk about the lessons learned, what did the data show us, and then we propose a solution, how to minimize. We cannot eliminate it, but we can minimize such the performance degradation and how to look at it in an optimal point. And we look at the effect of such a policy-based controller and show the results and the gain in efficiency. When I say efficiency, it's both with respect to energy saved and the less IO delay. And we'll conclude the topic after that. Backup and retrieval storage systems are growing. Predominantly hard disk-based systems are growing at petabytes a day. There's enough data from every data center, every provider, Oracle, Amazon, Google, Facebook, Microsoft, about how data is growing and growing and growing. Number two, predominantly this data stays on a hard disk. As much as we would like to think that the solid state devices and all the wonderful technologies of today's storage is coming to play with low latency and static devices, hard disks play a predominant part because this is where all your dominant data is residing. And because of that, all your HPCS applications, big data analytics, which depend on terabytes and terabytes of information, is sitting on spinning disks. And with this spinning disks comes the problem of hidden latent components affecting performance degradation. And why are these components affecting your performance? We'll go slowly one by one. Power components, mechanical components, thermal characterization, and how they individually play a part and how they collectively play a part. Individually play a part, there are a lot of research papers who have worked on it. It's dominant, it's visible, nothing special about it. But collectively, when you put everything together, the degradation is so bad, and we'll show the performance as a function of energy consumed to do the total work. And when we look at it, we'll talk about passive energy, wastage energy, which we don't want. Number two, we are to make maximum utilization of the active energy, the active current, the active power. And then we want to reduce time. So I'm looking at energy as a function, not power, not time, not current, not voltage. Energy as a function to complete the entire work done. And then if I do it correctly, then my degradation effects should be low, my QoS violations should be minimum, and the energy spent should be optimal with very less wastage. So looking at the challenges of QoS and SLA, although these are backup devices, although these are back-end storage, these are still mission critical applications because your data as a corporate, as an enterprise, as a HPCS application, as a big analytical application, is sitting on the back end, spinning disks, hard disks, and they can only tolerate about 5-6 minutes a year, 6 minutes a year. And these constitutes a big amount of user population, 20-25%. I'll not go in detail into each of these, but this statistics, this data points are available in our paper. Please refer to this and look at where are these numbers coming from, why is this so mission critical, what is the effect of violating the SLA, and any inefficiencies in this computer storage system affects your business critical applications. And we all know it's not the CPU, it's not the memory, as much as we would like to hate the latency there. It's the hard disk and the data retrieval from the secondary storage, which adds heavily to the latency. And these disks are not just sitting there spinning your data. We know that these disks in the backend system are brought into picture to add more and more compute into it. For example, this data storage system should take care of compression, deduplication, encryption, replication, encoding, multiple copies of it. And all this is the work done on the storage system. So when I'm talking in respect to this paper today, we're talking with respect to work done on the storage system than on the computer. And when you look at the storage system by itself, the storage system, of course, there's a couple of hard disks depending on the vendor. And we give a brief table here, could have 6 slots, 10 slots, and each slot can take, for example, a 10 terabyte disk, which is very common today. So you're looking at 60 to 100 terabytes, very simple, 60 to 100 terabytes on a single server box. And this box has its compute units, which consume power. It has fans, which have to cool the server units, and it has all the overheads of a traditional system. And these things are mounted on a single chassis, which means they all share the same mechanical characteristics. Okay, and because it's all operated on the same electrical power, the electrical power thermal characteristics affect each other. So we study the total effect of what's happening on the server, and we bring the whole picture into play. So in order to understand this and the dynamics behind it, we used the CPU and disk intensive workloads both together. And we have it in detail on what are the very familiar workloads which we ran through. CPU intensive bzip and disk intensive TCP/H queries. And we stressed both the CPU and the disk hypo components. CPU to understand the power consumption and the thermal characteristics of the power, very well known, but we studied it and we understood the wastage and the active part of it, and the CPU stalling or operating at lower utilizations. On the disk side, we looked both at the thermal characteristics and the mechanical characteristics, how one thermal characteristics is coupled and affects the mechanical characteristics of the disk, and how that affects the disk throughput. And then we recorded all the data to understand this intercouplings and understand what is the relationship between electrical power, CPU utilization, heat produced, cooling demands, fan speed, airflow, fan power consumption, vibrations, which are transmitted on the same chassis through the disks, and the disk inability to service you at the full speed because of the high density of the disk package system and the low micron granularity between the disks and the spinning head and the read-write head, everything. It has to do a lot of IO retries. So from this, I'll go step by step into what we did and how we studied it. So slowly going through, okay, initially, we looked at the CPU component, and it's very well known that CPU contains idle currents. Idle currents constitute to idle power, and idle power basically is wastage power. It doesn't do any active work. And we also know that idle power, idle current is a function of temperature. The higher you operate the CPU temperature, higher is the idle current and higher is the idle power wasted. And that's as much as 40% in modern CPUs. So you have to reduce the idle current and idle power. But in order to reduce the idle power, you have to cool the CPU, which means you have to spin the fans at a higher speed to let the airflow extract that cooling. But there's a fine line where as your temperature goes down, because you're cooling and cooling more and more, the idle current goes down, but your fan power increases. So there's a junction wherein these two come to an optimal point, and that's what we show here. A junction where the idle current can go down as a function of temperature as you cool it more and more. And this is the temperature, is the CPU temperature. As it increases, you have to cool it more and more and more. So your fan is consuming more and more. As your fan consumes more to cool it less, the positive effect is the idle current reduces. So there is a fine line where it takes a V-shaped curve. So we looked at this, and the details of the data points, the data collected, the workload executed is in our paper. So that's on the CPU component, the wasted fan power and the wasted idle currents and idle power. Number two, at higher temperatures, the CPU will automatically spin into DVFS, very well known low frequency. Low frequency means your workload takes more time to complete, which is again wasted energy, not power, energy. So now, if you look at the effects of your CPU cooling on the other component and the storage, which is your disk, because the spinning blades of the fan, which is pulse width modulated, very intelligently controlled because of today's intelligent cooling systems, the fans induce vibration. Higher CPU temperature, higher is the cooling demand, higher is the airflow, higher is the fan speed, higher is the fan power. Higher the fan power, higher is the vibration on the chassis. Although the disks today are mounted on vibration inhibiting components or vibration reducing components, vibrations are not down to zero. Vibrations affect the hard disk, and that brings down your I/O throughput. Because of today's high density, highly packed hard disks, there's a lot of retry because of vibration induced errors, very well known. So now we have a third component and a fourth component, and that's graphically shown here. As your vibration increases, the disk throughput goes down, and the energy used to complete the work is more. We have one more graph in the paper which clearly shows that as your fan speed increases, as your vibration increases, the disk throughput reduces. Very well studied, very well documented. I would like you to go through it if you want more details. Number two, as your fan speed, vibration is a function of fan speed. As your fan speed, the percentage RPM goes up. There is a point where the throughput, which was very high initially because your fan was low and vibrations were low, disk was very well damped, very well include. It will go linearly up to some point, flatten out, but then you will see that after a certain threshold, the slope of the curve increases and the disk will go into a bad I/O zone. This is what we call in our controller as a temperature zone, where the I/O is independent. Disk I/O is independent of the fan speed, independent of the vibration, so it can sustain a good throughput at a certain level. And after certain speed, as it increases, the vibrations are very well experienced by the disk. It's no longer independent of it or no longer visible to it, and those will clearly show an effect of this disk throughput going down now, which means the disk is doing a lot of I/O retries, which is nothing but waste of energy and waste of time. So now we're looking at the inefficiencies as a cumulative effect. Cumulatively speaking, if you're operating this CPU at a higher utilization, whatever, because your storage system is doing deduplication, encryption, compression, and eraser coding, or some analytical function, or replication, it's basically stressing that CPU in that storage system. As it is stressing the CPU in the storage system, the CPU consumption is high, CPU utilization is high, CPU temperature increases. So automatically the demand would be, I need to cool the CPU. But the penalty for that is you're spinning the hard disk, the fans at a higher speed. So that's wasted power, wasted energy to cool the CPU. If you don't cool the CPU, then the idle power will increase. Again, it's estimated at 40%, 50%. As temperature increases, CPU idle power is wasted. And higher temperature, the DVFS kicks in and CPU is operating at a lower speed, lower frequency. So you have to do more time. Basically, all this cumulatively adds up to wasted. It's all passive power, passive energy. It doesn't do any good. But now if you want to control the fan speed because you think that's wasted energy, you let the CPU operate at a higher temperature, you're wasting idle power. If you spin the fans and control the idle power, the fan speed is basically wasted energy, but the fan speed at higher disk will also introduce disk vibrations. Disk vibrations will induce higher IO errors and IO retry, and basically disk throughput reduces. So in order to get the same data, your now disk is taking probably double the time to retrieve the data, which means data latency increases. As much as we want to reduce the application latency, okay, CPU latency is minute, primary storage memory latency is minute, but the big latency is coming from this backend storage or the disk storage. And now you're doubling it, which means you're worsening the problem. So more and more time, energy is wasted in these non-active components, which these passive components are basically chucking up all your inefficiencies. So an optimal point, you can't eliminate it, but an optimal point would be somewhere you have to minimize this wastage. You have to bring down the temperature just enough so that the fan speed is at the optimal point, not to induce vibrations, not to induce disk IO errors, and to increase the disk throughput so that the IO time of the disk will reduce. At the same time, your temperature should be just enough so that your idle currents are not high temperature dependent currents. So you are basically looking at an optimal point. You can't eliminate it, but you're looking at a point in the curve among this 5 or 6 or 7 multiple parts which affect your inefficiencies to a low point where your application speed increases and your server efficiency increases. So server efficiency takes a different meaning. It is a combination of all these wastages, not DVFS alone, not CPU utilization alone, not CPU temperature alone, not fan speed, not disk throughput. It's a combined wastage of all this is what defines your server efficiency, what defines on how your storage system is operating or retrieving the data. So in our EADC controller, we took all the physical numbers, which are built-in data points, built-in instrumentation. So it's not depending on something outside. So we get the temperature of the CPU, the voltage at which it's operating, the current, vibrations is a function of fan speed. Fan speed is a function of fan power. We know that. So we take all this measured or inferred data, physical data, and then we know the CPU statistics, how much is utilization, what is the CPU doing, how much is the disk IO, readily available CPU or operating system statistics. And then we look at the application itself. What is this doing with respect to response time? And we feed this to a controller which will hunt. It has to hunt for this optimal place where the wastage is minimized. You can't eliminate it, but you can bring down to an optimal point where the combined effect of fan power, vibration, disk IO retries, leakage current is minimal. And then you throttle the CPU and throttle the fan controller both. So there are 2 independent controllers to put a cap on those controllers such that this entire finite state machine will look at the thermal power and mechanical characteristics together and bring it down to a most optimal condition. And the details are in our paper, refer to it on the policies and the different thermal couplings, how they affect how the policy controller works. And then as a result of that, how does the overall EADC controller look against these workloads that we executed and against commonly known benchmarks. For example, dynamical thermal management looks at DVFS controllers and what their policy does, and workload migration from CPU to CPU so as to elevate the maximum core temperature. Okay, and then we looked at JETC, which looks at core scheduling, memory activation, fan control together, but it eliminates, this particular study eliminates IO degradation because of disks, retries, vibration-induced performance. So overall, our study includes two clean parameters. One is the amount of energy saved, because I'm saving both power and time in these wasted components, and I'm increasing my active work done. And we show that our EADC controller does better in most cases, neck to neck in few workloads, few cases. And these are different server characteristics depending on different server models we picked up. And then second component is the delay, reduction in delay. That means how fast your application can complete the work, end-to-end work. And of course, our controller throttled both the CPU and the fan so as to reduce the predominant latencies and disk IOs and retries and increase the throughput. And we could complete the work much faster and reduce the delay, which is a direct reflection on energy. So again, I ask you to go through the paper, look at all the details. We went through the study of this entire coupling in a storage system. Why are they critical? What are the energy components? What is the energy budget? How it's done? Why are these SLAs and QoS important in different scenarios? And the combined hidden effect of these latent parameters completely visible, but we looked at it in a collective way and how they affect performance and energy, and our policy controller, which shows how the two controllers control the fan speed to control vibration and leakage and wasted energy, and increase the disk throughput and CPU throughput so as to complete the work faster. So the end-to-end goal is there. And a word of advice, as much as we have seen that policies or mechanisms or controllers to decrease disk IO, to reduce the penalty of fan power, which is wasted power, or to have a better DVFS control, or to reduce idle power, idle currents. It's the combined effect, because each of these components by themselves are such a big percentile of the total server utilization that you look at the combined effect and look at the optimal point to waste it. So that's our paper. You can reach us back at the email address given. And thank you for your time. And we enjoyed presenting our studies at this paper and look forward to interacting with you again. Thank you.